go start recording. So, as always, I'm only gonna be. I have Discord open on my second screen so I can see if you type something. Don't type in ELE404 chat because I can't see that. I only have the VC chat open. So if you have like something comment, just type it in VC chat and I will see. Or you can just unmute yourself and talk. So I'm going to be covering over basically. I can't see. Yes, I'm blind. I'm going to be covering over basically everything MOSFETs for the finals. So for future reference, because I know some people watch my videos in future years, this final is post-midterm, so it's only MOSFETs. I know that some of the previous finals have been like combined, so there are BJTs and diodes on it. We're not doing that. We're just doing MOSFETs, right? So actually, this is a lot simpler than previous years. I don't know if any of you have seen the previous year's finals. They're kind of really bad. So yeah, we're only going to be covering MOSFETs. And I know the way that the professors teach you is they try to teach you every single specific scenario of MOSFET you will see. I don't do that because there's an op amp on one of them. That's awful. I don't want to do that because it's just way too much to remember. What I want to teach you is how the MOSFETs work and how you can use that to apply to any MOSFET you see. I want to teach you the sort of fundamentals so you can handle any MOSFETs, even if you forgot, oh, what's a source follower, what's a that common gate, all of that fun stuff. So let me pull up my notes on my other screen so I can also run through them. Those are not the notes I wanted. Shoot. Okay, there you go. So obviously we're just going to go over MOSFETs first. And so we're going to start with just the NPN MOSFETs, and then we can apply everything to the PNP MOSFETs. If you know anything, the NPN and the PNP are practically the same, but you flip all the polarities. Right? So for an NPN, current goes from the drain to the source. For a PNP, it goes from the source to the drain. The VTN is going to be negative. This is going to be positive for NPN. And VTP is going to be negative. That's why usually we just write VTP is going to be some positive number, like so-and-so. Right? Whoopsie. And what's the other difference? Right, how you draw them. This is your gate, that's your drain, that's your source. The PNP is the exact same way, except the arrow is driven the other way. And this arrow is very useful because it tells you where the current goes, right? The current goes from drain to source or source to drain. Everything else is the same. That's it. You just flip the polarities, right? So all of the other rules you'll see, it's practically the same. Okay, so MOSFETs have 4 terminals. It's P-type, N-type, yeah. I think we just refer to NPN, do we? Do we ever refer to it as P-type, N-type? Really? Damn, I'm stupid, sorry. I thought it was the same thing. This is P-type, right? Right, NMOS and PMOS. I'm sorry, everyone. It's an NMOS. NPM is the BJTs. I got so stuck with that. This is the correct ordering, right? NMOS and PMOS. I always mess them up. If you couldn't tell, I'm not good at remembering terminology. Okay. So, there's 4 terminals of a MOSFET, driven like so. There's a drain, source, the gate, and the base. We don't usually worry about the base. The base is usually connected to either lowest potential or highest potential. And correct me if I'm wrong, it was sort of, I don't think they ever mentioned this. I believe lowest potentials for NMOS and highest potentials for PMOS. But the point is, if it's not drawn there, you don't have to worry about the base, right? Unless they start doing funky things with it, and that's when you get the body, what's it? Body effect. Wow, I forgot the name of that as well. Jeez. Anyway, so this is the body, drain, gate, and source. Obviously, your on mode is going to be we'll go over a body question. It's not that much. It's not that much more. It looks a little scary. Trust me, it's not that bad. On occurs when VGS is going to be greater than VT, than the absolute value VT. Or is that how they drew it? Let me check. Just to make doubly sure. Yeah. So VTN or VGS is going to be smaller than VTP. Or sorry, is that positive? Let me think. Yeah, it's positive. Yeah, that's correct. VGS should be smaller than VTP for NMOS. VTP is the threshold voltage for a PMOS, and VTN is the threshold voltage for an NMOS, right? So this is threshold. The N and P just represent negative and positive for NMOS and PMOS. So you have that. They are in your formula sheet. They are. I just want to really make sure you all know this. For saturation, it needs to be on, plus you need to have and you need to have VDS is greater than or equal to VOV. Now remember that there's 2 ways to solve VOV. Usually people just remember the first way to solve VOV, which is VOV is equal VGS minus VT, absolute of VT. That applies to both positive and negative types. But there's a second way of solving VOV, and it's a little hard. You need to know it. You need to know there's a second way because it's not obvious on your formula sheet. If you pull up the formula sheet, it's over here. You notice there's a VOV here, VOV here. You need to take this equation and that equation and rearrange it and then substitute that in. So it's on your formula sheet, but it's also kind of not on your formula
downstairs
sheet.
the game and a Bungie. Having said all of that, I walk away from my time.
This dude. I don't want to have to spend time editing out if someone like unmutes and then says something really stupid, because that actually takes a lot of time because I'm kind of dumb on editing. So try not to cause too much of an issue. Or post stupid shit. I shouldn't need to tell you that. Anyway, the second way of solving VOV, again, not on your formula sheet explicitly, but you can solve it using the formulas on your formula sheet, is that VOV is equal to 2ID over Kn W over L. Or this is also the formula for current, right? I believe, yeah, you could just rearrange your formula for current for finding that. So as always, your VTN. Oh, Kn apostrophe. I'll get to that in a minute. I'm very annoyed about that. VTN and VTP, usually represented as absolutes, is your threshold. The Kn and your Kp apostrophe, these are your transconductance. And then your WL, either denoted a PN or a P, depending on whether it's positive or negative, as always. This is called your aspect ratio. So I want to make a note about the formula that ID is equal to Kn apostrophe W over L VOV squared. Because, and this is very annoying, the two professors, Jassar and Valente, do it differently. I have emailed Valente about this. I don't believe he's gotten back to me. I could double check right now. No, he has not. Of course he has it. It's Saturday. Okay, so whenever Valente does his work, he'll just assume that these two are the same. It's very easy to make this assumption. Jassar does this. So yes, this is what I mean. I'm in Valente's class, so I never considered this apostrophe thing, right? It was always just sort of there on the formula sheet. And Valente uses them interchangeably. Jatsar does not. And I don't know who's correct or what's even the difference, because in the question you might be given Kn is equal to, say, 400 milliamps per volt squared. Is this Kn W over L, or is this just Kn? No, I'm in Valente's class, so all of my reviews based off Valente. Because Valente is a coordinator, I'm going to be assuming this, but generally speaking, online, correct. This is correct online. Is K Valente is this, but is Kn in the same case? Yes, that's what I'm saying. But in a question, if you're given one of these, if you're given this Kn, you don't know which Kn. No, he's not, because in Jassar's slides, she will also write that ID is Kn V over V squared. Half. Sorry, I forgot the half here. So for this, again, I would recommend you make double sure. But for this study hall, we're going to avoid Kn. Because I don't want to cause more confusion than there already is. I don't know who's correct. And you could say, Jassar is correct, but Valente is a course coordinator. So you take it up with him. He hasn't responded to me. So, where were we? Right, yes. Okay, so that's that's like our base MOSFET case. You all should like know this already. This is physics level stuff. Oopsie. Okay. So now we need to talk about body effect, right? Body effect. Now, in a question, if you see the lambda is equal to 0, that implies no body effect. Or ideal. Right? So when we pull up the graph, if we pulled up a graph here, right here on the top, we have your current, and we have VDS. You should generally expect a curve like this, right? This is your ideal curve. This is your saturation key. This is your saturation point. And after your saturation point, your current is constant. However, that's not what happens in reality. In reality, you're going to get a curve a bit like so. So as L gets larger, it's going to be closer to ideal. As L gets shorter, it's going to be steeper, so to speak. And this is plus body effect. And then there's this weird line here. If you go back far enough and you hit 0 point, this is called VA. And your lambda is 1 over VA. VA will always be given to you. I don't think I've seen any question where you need to actually figure out VA. But you should probably at least know this one. Right? So that's why we say when lambda is 0, there's no body effect or it's ideal. Because that just means VA is effectively infinity. It's flat. So I'm going to... I'll show how that integrates into the models. But I'll first discuss the biasing. Sorry, was this body effect? Sorry, this is not body effect. I'm stupid. This... Oh my god. I forgot what this is called. I just keep forgetting terminology. I'm making myself look like a fool. Sorry, guys. Where did I write this down? This is output resistance. Or channel with linked modulation. Thanks. Come on, I wrote all of that and none of you guys corrected me. Okay. And second part is body effect. This is the other component that will affect how your MOSFET operates. This is body effect. Jesus. So what body effect is remember how we had this B here, right? This is gate, this is drain, and this is source. Actually, the type doesn't matter. Actually, let's just do this. If there is a voltage difference, so if VBS is not equal to 0, then you have a body effect. This here is kind of implied. So I'll just mark that as implied. Remember, the body is always connected. If it's a NMOS, it's always connected to the lowest potential. If it's a PMOS, it's always connected to the highest potential. So if there is a voltage difference between, if S is not connected to ground, basically, there's going to be a body effect. So how do we handle a body effect? Well, we do that in the AC equivalent pi model. So this is one thing I must note. Body effect must be solved in pi model. There is a T model with body effect, but we're not taught it for some reason, so I'm just going to go off what they've taught us. Just use a pi model. So now if we have our actual AC equivalent, we can now draw AC equivalent models. And the first one, we're going to cover the T model, right? This is G. You need to remember this, by the way. This is not on your formula sheet. It's not going to be handed to you. You just need to know it. So you actually have to remember this part, which sucks because I don't like remembering. This is your body. This is your drain. And this is your source. Frankly, at this point, this is not a pi model. I don't know why it's called a pi model anymore. It initially did, but we just start tacking on so many things. It no longer looks like a pi model. Oh, sorry. GMB VGS. And this is GM VGS. Note that GMB is not equal to GM. These are two different values. You can't simplify them. You can under some conditions, not otherwise. If this is a pi model only if it has CLM and body effect, yes. So this component here is your CLM, right? You can remove it if you do not have it. This component here is your body effect. So you can also remove that if you do not have it. So say if you know for a fact that your CLM is 0 and your body effect, oh, I should have said, if you see gamma is equal 0, this means no body effect. And your gamma is 0, then you can literally just simplify this into gate. This is your current source. This is your S and your G. Oh, sorry. Oopsie. This is your drain. This is your gate. That's about as simple as it gets. Actually, I think if yeah. Wait. Yeah, okay. So that's as simple as your pi model will get. This is your pi model. Full pi model. And then you have your full T model. So again, there is no body effect there's no body effect T model that we're taught. So if you have a body effect, don't use the T model. And it looks like so. You have your current source. This is GM VGS. You have VG here, just VG. So that's the actual current going in, right? Or I guess we can just denote that as G here. This is G, this is D. The current traveling through here has to be 0, by the way, right? And then you have a resistor, which is 1 over GM. And then you have your source. Yes, but you have to remember that sometimes you can't. So the question was, if you decide to use T or pi model, would you still get the same answer? Yes, but you have to remember that sometimes you cannot use a T model. The only difference otherwise is that it's easier to do the T model sometimes, and it's easier to do the pi model sometimes. The general rule, so if you have body effect, use pi model if you have body effect, and you use the T model if S is not connected to ground. So if S is connected to ground, it's recommended to just use a pi model. If it's not connected to ground, use a T model. If you have a body effect, use a pi model. Hopefully that's not too confusing. R in the source. Oh, sorry, RO. Yeah, okay, that's actually an easier way of writing it. Resistor. Sorry. Actually, use if resistor after source. The T model also looks simpler in my opinion. It's easier to do stuff in it. But again, you'll get the same answer. You'll be fine either way, whichever you choose. So again, this is a AC equivalent. What if it's connected to ground through a resistor? Yeah, that's the same thing. Use pi if there's body effect? Yes. So say if you had, after S here, you had a resistor, ground, sorry. Let me show some examples, right? If you have a MOSFET here with a resistor, then ground, use T model. Because there's a resistor after ground. Or resistor after source. If there's a body effect, like so, and you're told that gamma is not 0, use pi model. The pi model for NMOS and PMOS are the same. Yes. Actually, the only difference is the direction, right? But VGS is already going to be negative, so that factors into it already. So it's the same thing, really. For the variables, you consider it different. I'm not sure what you mean by that. So, yeah, again, the only requirement is if you have a body effect, you have to use a pi model. But generally speaking, we could just assume that the body effect isn't there, but just make sure it says no body effect. Okay. Current source always points down regardless of NMOS or PMOS. Yes, but you have to remember if it's negative, then it flips direction, right? So if you have here a you're going to have this current source here that's GM VGS, right? In a PMOS, VGS is going to be less than 0. So the current's going to be going up. You see what I mean here? Because this is actually a negative value. You can rewrite this as the absolute value, negative of the absolute value VGM VGS for PMOS. Or sorry, no, absolute value, sorry. Because you're just playing around with the direction. For an NMOS, VGS is going to be positive anyway, so it's going to be going in that direction. Now, another thing is that I know Valente, he likes to do this slightly differently, this body effect. He likes to do, pointing up, GM, V. I just realized, oh my god, I'm so sorry. That nearly did me in. VBS. That's not GS, it should be VBS, because you're talking the body, right? Valente likes to do this. I disagree with him, but they will both work. I don't want to keep that because it starts confusing people. If it's absolute value, shouldn't it point down anyways? No, because the current is going up. So say, let's give an example. Let's say that our GM comes out to 0.4 amps per volt squared, and your VGS is going to be -4 volts, right? Then you do that. What's VGM times VGS? I need a calculator for this. I'm kind of stupid. It's -1.6. So this is going to be a current source going down with -1.6 amps. What is that? 1.6 going up. You see what I mean there? Yeah. Okay. So remember, there's no unique formula for PMOSs. Everything just sort of flips, right? And it just flips naturally. It's not like I need to draw a separate pi model for PMOSs, because if you use a PMOS, or if you use a PMOS and NMOS, it will just naturally flip because VGS will flip, and because VGS flipped, this will flip, so on and so forth. Okay. So yes, you could just keep the direction down. Again, the point I'm trying to say is just because the direction is down does not mean that the current will be going down. Because if the direction is down, but there's a negative current, or there's a negative current, this is negative, then the current will be flowing upwards, right? It's just like how I can have this voltage source with -4 volts. What does that mean? This is actually the positive side, and this is the negative side. It's just polarity, right? Okay, the next bit is integrated circuits. Sorry, is there any other questions? Um, most of the amp we dealt with NMOS. Yes, you'll primarily do with NMOS. So PMOS always points up and NMOS points down. Yes. Well, they go the same way as you can see in these diagrams, right? You know how we draw these arrows here for NMOS and PMOS? The current flows in that arrow direction. Did I go silent? Sorry, can you hear me? Oh no, I think he's, yeah, okay. PMOS will always flow from drain to source. Sorry, NMOS. NMOS will always flow from drain to source. PMOS will always flow from source to drain. Just follow the arrows, right? So going back to the pi model, you can see here the drain and the source. For NMOS, it'll always be flowing down. For PMOS, it'll always be flowing up. Okay. So next bit are integrated circuits. Integrated circuits are fun. Integrated circuits is when we use one circuit to drive the gate of another NMOS. And usually they come in NMOS pairs, right? So you'll usually see it in something like this. You're going to have one circuit here with a MOSFET. We can connect this to ground here. Oh, sorry. And then we can use that to drive the output of another MOSFET. So we're going to call this ID2. This is M2. This is M1. We have ID1. We can use this to regulate current. And it can be used as a current amplifier. And we write under here the current ratio. So say ID1, ID2. In example, you could see 1 to 1. That means whatever current is flowing this direction is going to be flowing that direction. Sometimes you will not be given that ratio and you'll be asked to figure it out. How do you figure out that? Well, using this formula, and this one isn't on your formula sheet. ID2 over ID1, although you can figure this one out yourself, right? Using the current formula, it's going to be W over L2 of W over L1. So the aspect ratio of the second MOSFET divided by the aspect ratio of the first MOSFET. Is this a current mirror? If it's 1-to-1, it's a current mirror, right? If it's not 1-to-1, it's not exactly a current mirror, right? I don't know. Jasar calls it current steering and current mirror. That's interesting. I don't know. Maybe I just misheard how Valente was calling it. But as far as I know, Valente called this an integrated circuit and just sort of moved on. But with multiple current mirrors, that's interesting. Okay. So the other thing is that this is ideal. This is ideal where we have no body effect, right? If we do have a body effect, it's different. And with the body effect, I don't think we need to memorize this. It's going to be W over L2, over W over L1, over 1 plus lambda VDS2, 1 plus lambda VDS1. So the point that I'm trying to make here, remember all the way back when I said here, longer L's make it more ideal, shorter L's make it less ideal. So you want to keep gathering those L's, right? So therefore, maximize L, lower lambda. Keep it ideal. Sorry, I should clarify. This is bad. Current steering. So, if you are asked to find this ratio, you can find it using this formula, and I would recommend you remember it. Oh, this is also known as K. If you're just given it, then you can figure out the current on this side, and then you can apply it to the current on the other side, right? So say you can turn this, you could solve for ID2 by just turning this into a current source going down. This is ID2 is equal to K ID1. Is that correct? Yeah. Where did I get 1 plus lambda VDS? That's just something you need to remember. Sorry, you just need to remember that. I don't think you need to know this. I don't think you need to know this, but you might have to, is what I'm saying. I don't know what's going to be on the final, right? All of this is kind of just saying to maximize L. That's all this part is saying here. Generally speaking, you'll have an ideal one. Also, it's going to get a lot harder. Okay, okay, the last bit of like fundamental info I need to go through before we can get through examples. Sorry, I've just sort of been yapping, explaining everything. I haven't even done an example yet. Is isn't the ID1 formula? Let me check. I always forget. I might be waffling, but I don't think they show like I don't think they show how to solve for current with um with the channel width modulation, channel length modulation. Sorry, I'm not really sure why. I don't think you really need to worry about that then. Okay. If you need to find it with channel length modulation, you're going to be doing it using this, using the models, right? Yeah, exactly. That's what I'm sort of saying. I've never seen them use it, so I'm just going to note here. I don't think you need to know this. It's just maximize your L. Don't have like a super low L if you're given the option. Anyway, differential pairs. I love differential pairs, don't you all? Diff pairs. This is like the last bit before we get through examples. The only thing you need to know about differential pairs is how to split them up. That's the whole point, right? So let's use an example of a differential pair because I think it's best to show you an example and then actually I'll explain the concept first and then I'll show you some examples. So the two main sort of things you need to remember. So take this as a circuit, right? This is a circuit. We don't know what's inside. And this is the opposite of that circuit. So if this is voltage 1, this is going to be negative voltage 1, right? If they are connected like so, what does that make this? This turns to ground, right? So if C and negative C are connected, it goes to ground because it cancels out, right? So that's the first example. Let me see. Let me just check my notes because I remember there is a particularly interesting example here. Okay, yeah. So that's correct. And then the second thing is that if you have two identical circuits, these are not opposite circuits, and they connect. Let's say you have some stuff after this, like so. This is the same as them not connecting at all. So remember, even if this is, say, connected, like this, let me reorganize this a little. They both go directly to ground, right? Because these two cancel out before the resistors even have a chance to get their job, right? If they're the same circuit, the identical circuit, then this is voltage and this is voltage. Nothing really changes. Nothing happens between them, right? So you can just cut them out entirely. You can cut that connection entirely. So the whole point of differential pairs is that we have these two circuits which are either the same or opposite of each other, and we want to figure them out separately. We don't want to figure out the whole circuit because that's more work. We would rather solve one circuit, and because it's identical or because it's opposite, we could just use that to solve the other circuit, right? It's the same thing. So here, if C and C are connected, it disappears. Connection disappears. So this is identical. voltages. And this is opposite voltages, right? This would be some voltage 1, and this would be negative voltage 1, so that cancels out. And this would be some voltage 1, and this would be some voltage 1, so nothing happens. And now we're done. That's actually it. That is all the single-ended concept. Oh, yes, single-ended concept. Yeah, the sort of cascode thing. The cascode thing is, oh, yes. I forgot about that. Thank you for remembering. I knew I forgot something on, like, my notes I was going to teach, but... Okay. So now we have the single-ended part. So that's represented as the amplification of, say, of a single end. This is part of differential pairs. Right? All that it is just want to make sure. Let me check my notes here. So if we have two circuits here that are identical, and we have some point here, this is going to be VO1 and VO2. Now, these are the same circuits. Therefore, VO1 is going to be equal to VO2. Right? But usually we define the VO as cross for them. So VO is going to be 0 in this case. But that's not really useful, right? We just want to see, what is the amplification of one of these. So the amplification here is pointless. Therefore, we find VO1 over VI. Or VO2 over VI, right? Because same circuit. And we call this ASE, single-ended. Ended. This is also differential pairs. Differential amps. Yeah, they are. As amplifiers. So we'll do some examples about this. Actually, we can do it right now because... Oh my god, I almost forgot. The rejection ratio. We need to do the rejection ratio. Okay, last bit. I think this is the last bit. I'm pretty sure this is the last bit. So the only thing you need to know about this is if you have a differential pair. So let me use an actual circuit as a differential pair without just using a big C so that I don't need to write as much. Actually, yes, everything is derived. I don't want to make you memorize stuff. I want to just I want it so that you derive stuff, right? Because it's easy to remember, but then you just sort of forget on the test. I can't remember anything. I'm sorry. I don't even know if I need to draw this. The whole point about delta G and delta R is that if you have one part of your circuit that's off, so let's say this is GM and this is GM plus delta G, or in this case, yeah, I'll go through derivations. That's like, yeah. Or in this case, if you have R here and then you have R plus delta R, you could still use the half circuit system, right? The half circuit is still a good approximation. And then you can what's the difference between these two? This one has a difference in the GM. So this is saying, okay, these have very close GMs, but this one has a small difference in GM. Sorry, this should be an M. And this is the same here. These two resistances are very similar, but they're off by a little, right? Because in the real world, we cannot have two resistors with the exact same resistance. There's always going to be some level of tolerance. And so actually, I don't think these are connected. Usually you'll just see like this, right? And when you solve these, you will get, oh, sorry, ICMR. I'm not sure what you mean by ICMR. The Vmax, Vmin. Yeah, I can go over that. We'll do a couple examples with that. So the half circuit here is still a good approximation, and we can find the the sort of amplitude of this using the same way, right? So this is still going to be minus plus VO, if I'm correct. Yeah, and yeah, I don't. If you're given a question about this, you will be given half circuit. You'll always be able to do half circuit, or else the whole point is kind of lost, right? So the amplitude, you could find the amplitude of these circuits, and we call that the common mode difference. So the amplitude, or sorry, the which is just V over VI. Again, you could solve for this. It's not something you remember. It's something you solve for. You have to rearrange the circuit, bring it all into models, and then find ACM difference. Now this is going to be small, right? Because these two circuits are identical. But you will have a difference because you have this minor incorrect part. And so this is the final thing. So CMMR, this is the common mode rejection ratio. I don't know why sometimes it's MMR. Usually it's RR, sorry. But these are interchangeable. Common mode rejection ratio. I don't know why it's MMR sometimes. I don't know where the second M comes from. So for example, you'll have delta G is going to be the absolute of the difference of the amplification difference. So this is when it's when they're operating opposite to each other. So this is going to be negative V, and the other one's going to be VI. God, how do I explain that better? I'm sorry. I should have thought about how to explain this better. So one second, let me just write this all out. When you see common mode, I believe that means that these two are the same voltage, right? This is C and this is C. This is common mode. Sorry. C and C. diff pair. Let me draw out the whole circuit. This is a proper diff pair. The voltages are going to be mirrored, right? So remember what I was going back a bit before, that what do you call if these two voltages are the same, then the voltage gain across here is going to be 0, right? Because it's the same circuit. The voltages here are the same, therefore the voltage difference is 0. We use this to simulate what happens if there's like a little bit of noise gets in, right? If both sides, both gates get in some voltage, the same amount, and we call that common mode. So when we say here the common mode difference is, okay, if we're working in common mode and there's this minor error in resistance in one side, what is the amplification gain? If these two circuits were completely, absolutely identical, it would be 0, right? Because if you get some voltage here, if you get plus 0.1 volt here and plus 0.1 volt here, the difference in VO, again, it's going to be 0. But these are not the same. So the difference in VO is going to be like, oh, I don't know, 0.001 volts, something like that. Again, we'll go through examples of how those work. I just want to keep in mind to you the ideas. So if you're just running and you just want to get the ideas in your head, I want to sort of keep them all in one place. So this is the diff pair operating opposite in normal mode, and this is common mode. Okay, we're done of not the study hall, just the actual concepts. So now we can get on to actual questions. Is there any particular question that anyone wants to go over? Cascode amps? I'm not sure what you mean by cascode amps. Can you give like an example? Yeah, those are just regular amplifiers. Okay. I'll cover how cascode amps work. And the reason why I didn't really want to go over them is because this can be derived. It's sort of just an extension of everything we have already learned. One of the where is it? Quite literally, all you need to know for cascode amps is this. If this is a DC source going into a MOSFET like so, and in saturation, this turns into RO. That's it. That's literally it. So let's say you have let's give the example cascode that they show in the examples, right? So you're going to have these two here. This is your Vin, so it's AC, right? And this is going to be some VB, right? It's some constant. And this is going to be your VO, your current source. Oh my lord, this is too cramped, sorry. You have your current source going down. So what's the resistance here? Well, this is in saturation. And we can figure out the resistance equivalent here. In this particular case, the resistance equivalent is going to be GM RO. If I'm correct. Let me just check. This one will make doubly extra sure. I forget how I wrote it down. Okay, correct me wrong if I am wrong. Yeah, okay. AVRO. Or AV is GMRO. Or I can check the formula sheet. 1 second. This is a common source. So it's RD. Sorry, no, not RD. Sorry, let me pull up the exact answer, because again, this can be derived yourself. I don't you can just derive it yourself. And that's kind of the whole point that I want to sort of drive home, is that I don't want you to memorize this stuff. I want you to just figure it out, because it's often faster to just figure out. Okay, yeah, so this is negative GM RO1. Negative GM RO1. We're going to call this M1, M2. So this is in saturation, so the R equivalent here is just going to be RO2, right? Well, what's that? This is going to be your VO. This is GM RO1, RO2. I'm sure you could figure that one out. Wait. RO is equal RO1. RO. I think, because it's a little weird what they do here. I'm sorry, I may have gotten something mixed up here. You can convert to AC. Yeah, you're supposed to convert it to AC. RO3. Okay, yeah, I think I was wrong here. Oopsies. Sorry, everyone. Because I'm just looking off of Valente's notes here. I'm burnt, yeah. Yeah, it's a DC current. GM2. What exactly is he doing here? Okay, I assume at this point I would just remember it, because I would have to actually solve through it. This is what Valente did here. So again, you could solve this just by going into AC mode and then just solving it manually. It's just finding for RO here. And then the voltage gain is going to be negative GM1 times RO. I'm going to have to review this, because I think I misunderstood it when I read over it. So I apologize about that. But again, you can do this in AC. You can just figure it out. You don't need to remember that, so to speak. Just using all the stuff we've already covered over, you can figure that out. Okay, so now we can get through to examples, unless there's some other concept that I've forgotten already. Is there any other concept I need to go over? Okay, is there any question or any part of this you guys want me to go through first? Because I have examples from pretty much everything. Oh. What's common mode gain and common mode rejection? Okay. So common mode, okay, so remember differential pairs, right? The whole point of differential pairs is we want to get this what would you call it? You want to get a voltage difference at this point, right? It's an amplifier, right? It's an amplifier. And to drive that amplifier through, we have two MOSFETs, one on each side, which give opposite voltages, right? So it doubles the voltage gain, and this is a differential pair. However, the issue is noise. When we have noise in, if say we turn off these two voltage sources, right? And we have some noise come in. What does noise do? Both of them drive through each side of it. So if noise comes in and increases this one by 0.1 volts, it's also going to increase this side by 0.1 volts. So this is what we call common mode, because both sides have the common voltage, the same voltage coming in both sides. Now, what happens in a differential pair when both of the gates get the same voltage increase? This part here might increase 0.5 volts, but this part here will also increase plus 0.5 volts. So the effective change is 0, right? And if it ended there, we can just say that the common mode amplification is 0. Because no matter what we drive in, there's going to be 0 amplification. However, in reality, we do not see 0. We see a little bit of change, and we call this the common mode gain and the common mode rejection rate. So when we have a MOSFET with, say, GM, each MOSFET has a GM, they're not going to have the exact same GM, right? That's just not how the real world works. So the difference here might actually come out if a VI is like 1 volt. The difference in VO might actually exist because it's the real world. And we note that down as the amplification of common mode, or the common mode rejection ratio, which is this formula, which you need to remember, or delta R for resistance, depending on what you have. If you have a resistance difference, or you have a transconductance difference. This is not transconductance. What is this again? What is GM? I forgot the name. Okay, does that answer your question? All right, awesome. Okay, you know, we'll go over that because those ones are perhaps the harder ones. Is it the harder one? Oh, no. Let us go through. All right. Let us do common mode rejection ratio of GM. CMRR delta G. And we're just going to derive. So we're not actually going to have any values here. We're just going to derive what is the common mode rejection ratio for a difference in GM. And I would recommend you do this. I would recommend you derive first and then you sub in all the numbers, because in my opinion, variables are a lot easier to work with than actual values because it's easy to mess up actual values and it's hard to notice that you messed it up. Okay. So we have up here VDD, two resistances. This is going to be R and R, the same resistance. We are going to have two MOSFETs on both sides. And because we're working in common mode, these are both going to be driven by VI. Right? There's not going to be a difference between them. This is going to be, this is going to be RD. And we're going to call this one here RS. And then we have GM here, and then GM plus delta GM. So CMMR delta GM is what? Kind of hard to start with. Oh, this is going to be negative, and this is going to be the positive side of VO. We're going to call this side 1 and this side 2. So whenever we need to differentiate 1 and 2. Right? Well, we could turn this into a, we could split this into a half circuit, right? Cut this down in the middle, and we can handle each one at a time. Well, they're mirrored, so we can handle one at just one side. And it's the identical to the other side. So let's turn this into AC mode, or model. We're going to have a ground up here with resistance, that's RD. And because we have something at the bottom, it's at RS, it's going to be T model, right? It's going to be GM, VGS. Oh, nearly forgot. We're just going to assume there's no body effect or channel length modulation. Oh. This is going to be 1 over GM, and this is going to be RS. And we have here VI. Is this a differential amp question? This is common mode rejection ratio. So yeah, it is. So what did I do? Oh, yeah. So what is the current running through here? Well, it's going to be GM VGS. That's it, right? On the right-hand side, the only difference, this is 1. On the right-hand side, it's just going to be GM plus delta GM VGS. It's going to have the same VGS because everything else is the same, right? And so we could derive here, like this part is irrelevant. Okay, I could do that question afterwards. Don't you have RO? We just assume there's no RO. Like the question that Imagine Dragon just sent, I'll do that later. Hopefully I can get it right. It will just tell you sometimes. Just assume that there's no problem here. You know, it makes things easier. Okay. Anyway, the current here, we know the current here now. It's GM VGS and GM plus delta GM VGS. Well, using that, we can find VO, right? The current here. Using the current here and the current here, we could find VO. The negative terminal, or VO1, is going to be VDD. Did I write DD on the top? Yeah. Minus GM VGS RD. And VO2 is going to be VDD minus GM plus delta GM VGS RD. And so what's VO? VO is just a positive terminal minus a negative terminal, right? And you do the math, it comes out to negative GM VGS RD. Or delta GM, sorry. Negative delta GM VGS RD. And now immediately we could find what is that? 1 second. All right, we need to find VGS now. Where's VDD? VDD is at top here. Okay, so what is VGS here? This is S, so this plus that is going to be VGS. But this is our VI, right? It's always best to represent that out, right? So VGS is just this difference. What is that? This is a voltage divider, right? We're trying to find the middle voltage between two resistors. And so we can determine that VGS is VI times 1 over GM over 1 over GM plus 2 RS. And we can simplify this by multiplying everything by GM. You get VI over 1 plus 2 RS GM. Just multiply by GM. So VO is now negative delta GM. VI over 1 plus 2 RS GM RD. Okay, at this point, I don't need to tell you how to find the amplitude. You just need to isolate for IO, and this is for VI and VO. And eventually you'll come to ... Or should I go over it? Actually, did I? I think I just did in one fell swoop. All right. Yeah, you just move VI over. And then you combine it. So the common mode, because it's the same. Why are there two RS? Did I misread it? What the hell did I do here? Oh, sorry. The initial question had it written down too. Let me just remove that. I'm so sorry about that. Yes, sorry. It's because the initial question here had just one RS. I had only written down the simplified model. And actually, this is a good example. RS here, right? How do we split this up into two pairs? Because this is sort of combined. Well, remember, we're working in common mode. So this connection splits. But we can't exactly split this connection, right? Because there's still this kind of RS in the way here. We can split RS in two. We can remove RS and create two RS here and two RS here. Thank you so much for pointing that out, because I forgot about that. And once we remove that, because common mode, we can remove that connection, right? Going back to all the way down here at the bottom. Where is it? If we have two identical circuits in common mode, this is common mode, we can cut the connection. And so this simplifies into... Let me move this down. Let me make this a bit more organized. Sorry. 2RS. 2RS. Sorry, I hope that makes sense now. Because I skipped over steps. So yeah, that was correct. 2RS. So again, that's a use of that common node, as I was saying earlier. So that's going to be your VO. Now your ACM, your common mode amplification of, what is it? Yeah, the difference is going to be minus delta GM. You just move over the VI, right? RD. 1 plus 2 RS GM. And that's your common mode amplification. And oopsie. So the other part is, what is a CMMR or CMRR of delta G? It's going to be the absolute of AD over the absolute of ACMD. This is your working in differential, and this is working in common mode, right? So we know the south part, we know the bottom part. That's going to be, actually, we don't know what it is. Or we do know what it is, it's just this. The absolute value of it. But we need to find AD for this. One other thing that they note is that you could sort of simplify this. You could just remove the 1 because it's so small. But you don't have to in your final answer. So all you have to do is find AD, and then you could find the rejection ratio. Should I go over finding that? Because it'll be interesting, because I don't think I actually wrote down how to solve AD, but I could try it. RD. All right. Why don't we try solving for AD? Just AD itself. Yes, please. All right. So AD is what? Okay, so let's go back to our original circuit here. So now we're operating in diff mode, or differential pair. And you'll notice here that now we're working in diff pair. We solve this actually differently. Remember, this here, as it comes out here, we're going to have some negative voltage, 1, and as, or sorry, 2. And as it comes down here, it's going to have some positive voltage, 2. What happens when two opposites collide? Nothing. Gone like the wind. To ground. So we can redraw the circuit. VDD. Ground. VI. It's negative VI. Oh, it's no longer in common mode. We can erase that. And so now we can ignore this half and just solve each half separately. Let's put that into a Let's put this into AC mode. We don't have any connection down here, so it's going to be easier for us to just use pi mode, right? This is VI plus or minus VS, or sorry, VGS. Down, and then, oh, we don't have an RO. So this is going to be GM VGS. And this is going to be RD. And this is going to be VO1. Right? We don't have no RO. Well, I'll be damned. VI is VGS because this goes directly to ground. So VI is VGS. Therefore, our current is just GM VI. And therefore, what is VO? VO is going to be RD GM VI. Because that's just going to be the voltage difference from here, right? Is it negative? Yeah, I believe it would be negative, wouldn't it? I might be stupid. Yeah, no, it's positive. It's positive. Yeah, because this flows from a positive to a negative downwards. So everyone understands how we got VO here, right? That's it. We took the original circuit, we applied our differential pair rule, which is that it goes straight to ground. We cut out the second half of the differential pair because we don't need it. We only need to solve one side at a time. And we find that VO is going to be RDGMVI. Now, what about, this is just VO1. What about VO2? Well, it's the opposite of VO1. So VO2 is going to be negative RDGMVI. Now, what is VO final? Like, what is the total VO? VO is going to be VO2 minus VO1, right? It's a positive minus a negative side. VO is negative 2 RD GMVI. Is anyone sort of confused on how that came about? And also our amplitude of the differential pair is going to be negative 2 RDGM. Why is VO1 not negative? Because it has to follow the rules of a this current source goes down, right? So therefore, this is going to be the negative side. This is going to be the positive side. Has to be. Therefore, this is 0 to a positive voltage. That's it. Or this is ground. Right? Because current always has to flow from positive to negative. And this current source kind of forces it to flow from positive to negative. I think it is. Unless I'm waffling there. Am I stupid? No, I think that's correct. Unless my logic's wrong there. Because current flows that way. Oh, okay. I'm stupid. Yeah. I think my Discord just wasn't updating. It wasn't showing that people were calling me stupid. All right. I get messed around with polarities often. So yeah, you can do KCL, or you can logic it out. If you're me, I wouldn't recommend logicking it out because obviously I can't do that. That's going to be negative. That's going to be positive. And then you're going to end up with positive 2RDGM. There you go. Thank you, everyone. Yeah, I'm not really sure what. Yeah, you're right. You're right. It's going across the resistor in the direction of the current, negative RDG, negative. I was being very stupid there. My bad. Anyway, we know AD. We know AD now. That's what's important. That's what's important. Don't worry about my mistakes. I don't make mistakes. If I make mistakes, then I didn't actually make a mistake, and you're all wrong. So the common mode rejection ratio, delta G, is going to be 2 RDGM over this. And remember, there's a +1 here, but nobody cares. So you can simplify it out. There's some common things, right? So 2RD GM times 2RS GM over is that correct? Yeah. Times 2RS GM over delta GM RD. RDs cancel out. Your delta GM stays. Did I put in a 2 here unnecessarily somehow? No. Yeah, no, it's correct. All right. So you end up with for GM squared RS over delta GM. There you go. So you see, you could just remember the answer, but there's like 50 different ways to set this up, and you're going to get 50 different things to remember. Or you could just remember the fundamentals and just apply everything else. I hope I explained this question decently enough. Does anyone have any confusion? Hopefully that cleared up something for you guys. So you understand how common mode how you work common mode. You find the common mode amplification, and then you find the regular amplification in differential mode, and then you just divide them, right? The regular amplification divided by the common mode amplification, and we call that the rejection ratio. Okay, does anyone have a question they want me to do? Should I do that question that was posted earlier? Because it's also a it's also similar to this one, I believe. Let me see. Find RD such that should I do that one or should I do a different question? I don't know. No one wants to talk up. Do that one? Okay. I don't know where this question came from, and I don't have a solution for it, so I may end up messing it up, as always. consider the amplifier in figure 4. Let Kn W over L12 is equal to 2.5 milliamps per volt squared. Vt is 0.7 and no channel length modulation. Find the value of VDC. Where is VDC? Oh, there it is. At Kn W over L, find the value of VDC. I assume is that just like to put it in saturation? Maybe I might figure it out if I just do it. So in DC analysis, this is going to be in common mode, right? So we can cut out the AC for now. Oops. You're going to end up with VDD, RD here. This is going to be the negative end and the positive end of VO. You have M1, M2, and both of these are going to be VDC. It's just going to be a constant VDC. And then, okay, here we go. We're going to have 1K RS here. Now, this is effectively common mode, right? Because both sides are getting the exact same current. So we could pull that same trick we did earlier. This is going to become 2RS and then 2RS. In case I didn't explain it earlier, this is the exact opposite of parallelization, where we're uncombining it, right? And if you do 2RS parallel with 2RS, you just get RS. And now, knowing that, we can now cut the connection in the middle, right? Following our common mode rules. And so now we can cut out the entire other half of the circuit. And we're just left with VDD, RD. This is a negative terminus. This is VDC. And then 2RS to ground. It's asking us what is VDC. Oh yes, you need VDC to maintain it in saturation mode, right? Because saturation is predictable and it's simple and it doesn't care about VDS. When you're in triode region, it cares about VDS. We get all of this weird funky stuff. It doesn't work linearly. So what this means here is keep in saturation. What is the DC value so that this MOSFET is always going to be in saturation? There's no channel length modulation. We're going to assume there's no body effect as well. All right. So we're back to DC analysis. What is that? VDD is 5 volts. What's VRD? RD is not known. Okay. VTN is 0.7 or VT, yeah. And 2RS would be equal to 2K. What's the current? Oh, the current is 1 milliamp. And because we're splitting it in two, that means we're going to have half a milliamp traveling through here. Okay. Well, we can now use the current formula, right? We know current We know Kn W over L. And then we have VGS, which is our DC. Actually, it isn't our DC. Oopsie, it is not our DC. Need to keep that in mind. Minus VTN squared. Half. Thank you. I was going to get doubled. This is our S. So what is VGS? Well, VGS plus the voltage difference here is going to be our VDC, right? So that would be the current times RS, which is ID. So that's 2 ID RS is equal to VDC, or VGS, which is equal to VDC. So now we isolate for that. That's going to be 1/2 of Kn apostrophe W over L. This is going to be fun. Oh, sorry, VGS. This is just going to be VDC. There you go. That's a bit silly of me. Sorry. So we can move that to the other side. We're going to have VDS minus 2 IDRS minus VTN squared. So I know this. Now we just need to isolate for DS. Oh, Lord. Or actually, we already know ID, so we can just find VGS first, and then we can find VDS afterwards. I don't like squaring. We're gonna have to anyway, right? The ID is 1/2 of Kn apostrophe W over L. This is VGS squared minus VGS VTN. Yeah. Plus VTN squared. Wow. I don't like quadratics. I don't. So you can move that over and you're going to get 0 is equal to VGS squared minus VGS VTN plus VTN squared minus ID over 1/2 of Kn apostrophe W over L. This is a quadratic equation. We can solve this, right? So 0 is VGS minus VGS. What's VTN? 0.7? 0.7. VGS plus, and this is going to be overcomplicate. Am I missing something here? Because I'm just finding VGS to find VTN. You're smart. See, I forgot my own equation when I was mentioning their VOV. I've done this several times before. I'm sorry. Okay. This is VOV as well. So we could just do ID over 2ID over Kn apostrophe W over L. It's funny because I told you guys to make a note of that. I said in the beginning, don't forget about this stupid equation because you always forget about it and then you end up overcomplicating it, and I did that. VGS minus VTN. We can move over VTN. Okay, so anytime you're solving for VOV, remember that equation, and remember just rearrange it. You don't need to do quadratic for this. This is VGS or VDS minus 2IDRS. You can move that to the other side. Okay, awesome. Put that into your calculator. 2 times 0.5 times 10 to the negative 3. What's kn apostrophe? 2.5. Okay, so I can move that. 2.5. You are saving me, Fire. I'm sorry. 0.7 plus 2 times 0.5 times 2000. And I'm getting 3.3. 3.33. 0.7 plus 2 times 0.5 times 2. Yeah, looks good to me. So there you go. That's our VDS. So that's our solution for A. Thank you again. Find RD such that AV is 8V over V. 2.33. Did I? Yeah, that's VDC. Oh, sorry, VDC. Sorry. Too many letters. Two times 0.5 times 2. Yeah, that's 2. I don't. Oh, sorry. ID 2RS. I was putting 2K here. I don't know how to use a calculator, if you can tell. I was doubling up RS before I doubled it. Okay. 2RS VDC. That's our VDC. So, oops. Let me just write here because I confused myself. RS is 1K. That's why I just saw 2 and I just put 2 in my calculator. Don't do that. Find RD such that AV is 8 volts over volt. Okay, so now we've been doing this in common mode, right? Now we need to solve for AV, which means we need to find VO and VO plus. So let's take this circuit again. Let's move it down over here. Back to our original circuit, and now we're working in differential pair. So VS over 2. Keep this in mind because over 2. VS over 2. So this is VS over 2, and this is negative VS over 2. This is a differential pair, not common mode. So now we operate differently. Remember what happens here. We're going to have some voltage coming down here. We're going to call it V2. And we're going to have some voltage coming down here. This is going to be negative V2. They're going to be equal and opposites. They collide, nothing. This goes straight to ground. And we're also operating in AC, so we simplify everything into AC. This goes to ground. And naturally, because we're in AC, we also use a model. We don't have an RS anymore. We got rid of it, so we're just going to use the pi model. And we don't have a body effect or channel length modulation. So let's draw it out. And let's get rid of this half. So we are going to have ground, RD. This is VO1. We have our current source and then ground. And then we have Vs over 2. Vs2 is directly onto ground. So this is GM, VGS, this is VGS. This is pretty simple, right? Although I did mess it up. So I have no right to say this is pretty simple. This is GM, Vs over 2. Current's flowing downwards because it's NPN. So VO is going to be, it's not negative, is it? No, it's negative. RD GM VS over 2. Is that right? Did I get the polarity right this time? And actually, VO2 is going to be RD GM VS over 2. Therefore, our VO is going to be 2 RD GM VS over 2. And therefore, our AD is going to be VO over VS, is going to be, these two cancel out. We get RD GM. So what's our GM? I already forgot. Our GM is, we don't have a GM. Oopsies. We need to find GM. What's the formula for that? I didn't finish DC analysis. That is my bad, as the kids would say. GM is KN apostrophe W over L VOV. Well, we know KN, W over L, and VOV. Do we know VOV? We don't know VOV. Well, we can find VOV. VOV is VGS plus VTN. VGS is just going to be VDC minus, is that correct? Yeah. So it's just going to be this half here. So if we find that out, we get 1.33. VGS is equal 1.33. You just remove this part here and it becomes VGS. Therefore, VOV is going to be 1.33 plus 0.7, 2.03. Is that correct? Hope so. VOV minus V. I shouldn't be trusted with formulas, just in general. I know all the content, but I always make these stupid mistakes. I got most of them down here, but they're not like compiled into one place. If you're asking for the formulas. Anyway. 2.5 times 10 to the negative 3. Of course, I'll post the PDF right after we finish. Times 0.63. We get 1.575 times 10 to negative 3. Did I fuck up my calculator here? No, I didn't. Yeah, VTN. So, AD is equal to 1.575 times 10 to the negative 3 RD. And we know AD, we want 8. That's what they wanted, right? 8? Yes, 8 volts over volts. Well, you divide. 8 divided by your answer, 5,000. It only took like 7 mistakes. That's why I have you guys. This study hall is not actually for you guys, it's for me, so that I can do the questions and then you can correct me. Part B? Sure. I'll just screenshot both sides here. There you go. Okay. Another example. Is there a particular question or area you guys want me to solve? Let me see. I'm looking through my questions, seeing if there's anyone. If there's any. Did I do part C? No, I didn't, because the common mode voltage, it's the same process as I did the first question here. That would just be this one here, the common mode output voltage. Just turn this into CM. I believe it's also single-sided then. They want to, yeah, they would want a single-sided one, because if it's not, then it's kind of useless. So here, all this is saying is find VO at VDC, VO1 at VDC, because that would be the VO1 common mode single-ended. Yeah, I'm sure you could figure that one out. All right, but we'll run through it just to make sure. Well, it's just this. Yeah, what Fire said in chat. So this point here is going to be VO1, which is just VDD minus IDRD. This is the answer for C. Okay. Holy shit, that's a big one. Let me see here. Oh, actually, it's not too big. Let me think. Okay, this is Valente then. Okay. That's incredible. Okay, so this is also a source, not mirroring. It's integrated circuits. So, for which yada yada yada. Kn is 400 microamps over voltage squared is equal 4 times Kp. I'm not sure why it gives a Kp, because there is no PMOS in here. This is unless yeah, they're all NMOS. I zoned for the last question, part B. Where did the RS go? The RS went because we're working in differential pairs. And remember what that means. If we have two parts connected like so, there's going to be, if we have the circuit here and the negative circuit here, right, we're going to have a negative voltage coming in here and a positive voltage coming in here. And because they're the same circuit, they're going to cancel out voltage minus voltage is 0, it becomes a ground. So we can erase everything connecting to it and just connect to ground. See how that works? Yeah. Okay. What must the bias be? So find GMB, GM, AVO, and RO. That's an interesting one. DC level shift between input and output of 0.8 volts. What must the bias be? Sorry, I'm a little confused. Where's okay? Okay. So VDD is something and VO is between input and output. This is going to be VDD minus 0.0 if I'm understanding this question correctly. It's a little odd. Okay, so this is a current steering or current mirror, whatever you want to call it, or an integrated circuit. So the first thing we want to do is we want to get rid of the other circuit, right? We want to, this circuit is not that important. We're trying to find the other circuit, and we want to be able to get rid of it. From Valent, VGS1 is equal VT plus VOV is equal 0.8. Yeah, well, I'm sure we'll figure it out somehow. So, do we have IREF here? For which we're not given IREF? All right. I guess we're not. That confuses everything for me. Okay. Well, the KN is the same for all of them. And the W and L are the same for all of them. So we can surmise that this is a mirror, right? Because ID of 3 over ID of 2 is going to be Kn of W over L over Kn apostrophe of W over L. These two values are the same, so it's just going to be 1. So this is a current mirror, right? So whatever current is coming down here is the same current that's coming down here. Let's simplify the circuit then. We're going to have the voltage source here. This is VI. This is VO. Oopsie. And this becomes IREF. Right? Because the current flowing down here is IREF. And therefore, the current flowing down here must also be IREF. Yeah, there's a lot. It's the actual concepts aren't too long, but then you combine in the questions and it kind of gets very, very annoying. What must be the bias be? Find GM, GMB, AVO, and RO. Okay. Oh, this is obviously the body. Goes straight to ground. Okay, so now we can turn this into AC mode, right? We're just going to assume this is on and in saturation. 99% of the time it'll work out because it doesn't really make sense otherwise often. So this is going to, oh, sorry. Now we have a body effect. So we have to use pi. Let's draw our pi circuit here. Listen, don't worry about curves. Just do the best you can. You know, I don't like to think too much about curves because it's not in your control, right? These are wise words from me, shit words, but they are not in your control, so no need to worry about them. So again, this is just memorization. This circuit needs to be memorized. This needs to be in your head. You need to have it knocked down. And okay, let's connect everything else. This is connecting ground. This is VO. Remember that current sources turn to open circuits afterwards, right? So we could just get rid of that. The what? All right, man. This goes to ground, and this is VI. Okay, awesome. So we need to find GMB, GM, and AVO. So GMB, oh, I don't know if I think I may have forgotten to write this down. Oopsies. Sorry. This is an important formula I forgot to write down the first time because I'm a little slow. XGM is equal GMB. Okay, VBS. So what do we need to find here? GM, GMB, AVO, and RO. Wow, I really don't know how. Can we find V over V? We don't know current. We don't know. Did this question have like full number answers? It did. Because we don't know the current. Unless I'm really missing something here, there's no current. We don't know VDD. What the hell? Oh. Oh, that's true. Okay, then we're not done with DC analysis yet. Oopsie. So let me move this down for now. Sorry, this wasn't one question I've seen before, so definitely not a nice question. I would not like it if this was on the exam. So we know that VO is equal VDD minus 0.8. So therefore, VGS is going to be 0.8. Gate minus source. Yeah, so VGS is going to be 0.8. VOV is VGS minus VTN. Or sorry, VGS. No, it's VDS. No? Oh, yeah. VDS. So VDS is 0.8. Yeah, because this is drain and this is source. Why is it 0.8 between input and output? I don't understand how that... Oh, okay, wait. So VDS needs to be greater than or equal to VGS minus VTN. Yeah, I'm aware of that, but... VDS is... 0.8 is greater than or equal to VGS or plus VTN. Oh, okay. Yeah, you're right. I'm stupid. I thought you were pulling that from somewhere else. It's VGS. Yeah, so this was wrong here. Oopsie. I was considering VDD the input. Okay, VI minus 0.8. So VGS. Okay, that explains a lot more. Okay. I made a very silly mistake at the start. That's why. Always silly mistakes. So that's going to be 0.8 minus VTN, which is 0.5. I just used a calculator to solve that. All right. So you get a VOV of 0.3. Now, what is GM? GM is equal to Kn apostrophe W over L of VOV. We know all these numbers. So it's going to be 400 times 10 to negative 6 times W over L. W is 12, and then L is 0.6. They're same unit, so you don't need to write that down. Times 0.3. You end up with 2.4 times 10 to the negative 3 for GM. So there's your GM. Now, GMB, oopsie, is equal to funky X times GM. We know funky X is 0.2, so you can just times that in. 4.8 times 10 to the negative 4. Oh, you're getting body effect, all right. I don't know what it's called, okay? It looks like a funky X. I'm going to call it a funky X. It's just like how this is a funky Y and this is a funky A. I don't know why the Greeks didn't just call it that instead of giving them these weird names like alpha and omega, gamma. So we know that. We know GMB. AVO. Okay. This one's interesting. So we're going to put this up like here. This is when we get into AC analysis. So AVO is equal to, well, you know this is going to be X GM. Or, yeah, XGM. Now, VBS is going to be negative VO, right? Because B is already connected to ground, and S is just VO. So B minus S. And then we have VGS. So VGS, as we said before, is 0.8 above. We know GM, we know XGM, we just need to know RO. Now, we have the formula for RO here. So RO is equal to VA over ID, which is 5 volts per micrometer. Is that the unit for VA? It's not, is it? Isn't it volts per meter? It's VA. It's VA apostrophe. I don't see a. What do you mean it's V? How? What do you mean it's VA apostrophe when they don't put a V in apostrophe? So VA is VA apostrophe over L. That's what he did in the solution? No? What do you mean no? I'm so confused what you're saying here. You're saying that's VA apostrophe, that's not even there. Oh. Really? That's awful. I don't. Valente never mentioned this, by the way. Valente has never mentioned this VA apostrophe. So I don't. Yeah. Okay, that makes sense. I'll put in my notes there. Is that from the formula sheet? Because I don't remember. No, the formula sheet doesn't have it. Oh, of course. Okay. I'll I'll keep that in the notes. I'll write that in the notes after because Valente has never mentioned this, and I'm very annoyed by that. Okay, so just in case anyone's a bit confused, VA is in units of volts per micrometer, and VA is equal to VA apostrophe times L. Okay, so VA. Thank you, Valente, as always, for never mentioning this stuff. So, whatever. 5 times the length is 0.6. Those units are the same, so they cancel out. So VA is 3 volts. So RO is going to be 3 divided by our current. We don't have a current. Okay. Now we're at another roadblock here. So we need to find the... Oh, wait. Do we? Yeah, no, we need to find the current. And, we can use the transconductance formula to find our current, can't we? Let me move everything upwards. Half of the problem is just remembering all the formulas so you know when to use it. Yeah, I know they're not same RO. I'm trying to solve for AVO right now. I'm not trying to solve for capital RO. Okay. So we know from our formula sheet, we have a formula here. It's square root 2kn apostrophe. Well, we could just use a regular formula, right? ID is equal to half. Need to remember that. W over L VOV squared. We have all of these numbers. 0.5 times Kn. This is KN apostrophe. Again, it's that thing from the very beginning. Kind of annoyed by that still. W is 12 divided by 0.6 times VOV, which is, what is our VOV? 0.3 squared. I forgot to put a times 10 to negative 6 there. Okay, that makes a lot more sense. So 3.6 times 10 to the negative 4 amps. That's a lot more reasonable. And now we could find RO. VA is 3 volts divided by 3.6 times 10 to the negative 4. And we get 8.3K. So we know our RO. We found our RO. We found our GM, VGS, and we know VGS. And we know all of these other values. We can now solve this circuit. What is VO? Well, we could just use current law. We have, we could just assume the direction of all of them are coming in, right? We can just do that. So let's write this on this area below. We are going to have 0 is equal to GM VGS, because that's just voltage source, plus 0 minus VO, right? From 0 coming across RO into VO plus whatever that is, VBS, which we know VBS is just negative VO. So we can turn that around to do negative GM VO. Now call me crazy, guys, but we can solve for VO. So let's move this to the other side. We have GM VGS is equal to RO plus XGM VO. We can then move that to the other side. So GM VGS over RO plus XGM is equal to VO. Oh, I nearly forgot. That's not, wait, what? VO is equal to, this is, I think I need to substitute in GS with something else. Its difference was 0.8, but that... Man, you guys gave me the hardest questions. I haven't seen this one before. So, oh no, we could just solve for VI. No, that's not correct. VGS is not VI. Oh no, we could solve for VO, and then we know what VI was. It's 0.8 plus that, so we can solve for that, I believe. Let's see if we're going down the right track. Let's not doubt ourselves. GM That's right. Okay. Yeah, you're right. That was it. I'm sorry. I think my brain is starting to just not work anymore at this point. So we can substitute that in for VI over VO. So this side here is going to be GM VI is equal to, and then now we can do GM plus 1 over RO plus that GM. I think I may have actually done just RO here before, which would have been bad. Now we can cut out RO because 1 over RO is going to be very small. Actually, no, we can't. I think we can't anyway. Let's just not. Generally speaking, you can cut out 1 over some resistance, but let's not just in case. Yeah, Valente does that a lot. He just sort of cuts out stuff because it's so small. Or actually, I was supposed to move it the other way around. So it's going to be VI over VO is going to be GM plus 1 over RO plus X GM over GM. And I can cut out RO here because that's going to be incredibly small. And we're left with GM. The GMs cancel out, so we're left with 1 plus X. Really? We're just left with... X is 0.2, so it's 1.2. Right. That's VI over VO. I'm sorry. I think this will be the last question because I think these are good enough examples. These are probably like the hardest ones. And I think my brain's already starting to fry. So this is going to be 0.83, which is AV. I always make that mistake. VI over VO instead of V over VI. So again, you only cut this out because 1 over RO is very small. About 0. So now we know 1 over AVO, and now we need to know RO. What is R out? Well, in this case, usually we just perform a that's all the work Valente showed. I just want to show this for the camera here. This is all the work that the professor showed. I mean, he's not wrong. That is the correct answer. Okay, so what is R out? So we're going to take this initial circuit once again. We're going to take our AC equivalent circuit. And what we'll do is we'll just stuff in a test voltage at R out. So we're going to turn everything else off. That's a voltage source, so that's going to go directly to ground instead. And we are going to put in our test voltage, Vx. And our eventual goal is that the R out, capital R out, is going to be Vx divided by Ix, right? This comes back to Thevenin. Remember when we did Thevenin and we had to find the equivalent resistance? I'm sorry, bring up bad memories, but... So, once again, we could just... Let's see here. I believe we can KCL this. Can we? Let me think here. Oh, yes. So this is going to be Ix. And we're all just going to bring these down. So All of these, we're just going to assume all of the currents go into the source. So we're going to have 0 is equal to Ix, that's the current flowing upwards, right? Plus GM VGS plus, oh, let me erase this for now. Plus, this is going to be 0. Oh, this will be on the finals, trust me. Valente did a couple of these questions. I wouldn't be surprised. Okay, I'm not going to say for a fact this is going to be on the final, but especially something like this output resistance, he's done this a couple times. I would expect this to be on the final. This is going to be 0 minus Vx, which is S. You know, let's just do S for now. We can fill it. Over Ro plus X GM VBS. So, what is VBS? VBS is actually identical to VGS, right? So VBS is equal VGS. Yes, this is just Thevenin where you add a test voltage. It's not Thevenin per se, it's just test voltages, right? We just learned them as part of Thevenin in 202, I believe. And they're just 0 minus Vx, so negative Vx. And then Vs is just Vx. So we can substitute all of that in. Ix plus GM. This is VGS, which is, sorry, so it's going to be negative GM Vx plus, or sorry, minus Vs, or 1 over Ro Vs, Vx, minus X GM Vx. You move them about, you turn them all around. What do you get? Ix is equal to GM, oh, sorry, plus 1 over Ro plus X GM Vx. And we want Vx over I. So we're going to move this down here and then that around. And we get 1 over all of this fun stuff. You can cut that out. XGM is equal to Vx over Ix is equal to Ro. It's the exact same process for the resistance input. You just put the test voltage on the input, not on the output. So does anyone have any questions about that? So this is actually 1 over GM 1 plus X. What's GM again? I forget GM. Good morning. 2.4 times 10 to negative 3 times 1.2. 350 ohms. Am I wrong? I'm wrong, aren't I? Did he just like forget about bias? Okay. I don't know why he just assumed there wasn't a bias, but I did. So I hope these examples and my initial sort of like explanations covered most, if not all, of sort of the post-midterm content. I know there's more I wish I could have gone through, but all of them are sort of repetitive in this step. You do the DC, and then you do the AC, and then you do the DC, and then you do the AC. The only other, everything else that you're being taught here is just extra bits on how to do that, right? So is there any other questions you guys want me to solve, or I think we can end it here? And I might add a little. I might add a blurb on how to solve minimum and maximum. No? All right. Well, I hope this tutorial was helpful for you all. And I hope you all do as good as you can on the test, because I know this is a hard one. I'm also studying my ass off for it. So I hope this is at least some good of a resource. I know that a lot of you won't be paying attention right now, but will be doing so after in the recording. I don't mind that. Just remember the equations, remember the process. Don't try to memorize each individual case. Learn the general understanding and then apply that general standing and you get quick at it, right? All right, have a good one, everyone. I'll upload this later.